Okay, so good morning. This is Control and Instrumentation from Northern College. This is week 7, I believe. Somebody can correct me if that's wrong. I think it's week 7. So I thought we'd start by quickly just going over what we've learned so far, and you can think about that, because obviously we're starting to head up to the exam now. We've passed the halfway stage, and you do have an exam, I think, on the 18th of December. Is that correct? Yeah. So we'll do that quickly, and then I've got essentially a new subject to introduce to you, which is not as difficult as some of the other stuff you've done, to be honest. So far we've looked at, I'll go through the contents list anyway, but we've looked at response with steps, we've looked at a response with a swept sine wave. So both of these methods are really looking at transients and changing conditions. The thing we haven't really done is analyse systems for steady state response. We can see the steady state response when we look at the transients, particularly with a step, because that's a transient followed by a steady state. But there is actually a method that's just specifically for looking at the steady state expectations of a system and what it's going to do in the steady state. So that's what we're going to look at today. Again, there's a wee bit of maths. It's not really too bad, I don't think, in terms of the maths. Yeah, that's all that is, really. So it's just another method for analysing what the system's going to do. Right, so if I switch over to PC view, and I'll turn the lights down a little bit as well. You can think about what we've already done and how much you already know, that we can kind of organise your revision. It's actually done. You're going to fall asleep if I leave it that done.
No, a bit darker.
A bit darker, then you'll definitely fall.
No, it's all good then.
VC, alright.
Right, so what have we done? We've done system modelling. So remember that was looking at the first principles, Kirchhoff's voltage law, Kirchhoff's current laws, Newton's laws, properties of resistors, inductors, capacitors, mass spring dampers. Putting them all together and building up a mathematical model of the system. So there's no controllers involved in that. That was just purely modelling systems on MATLAB or Simulink. Then we looked kind of in the same time, we looked at Laplace transforms, because most of your modelling equations ended up with differential equations in them, like voltage across an inductor is L times the rate of change of the current. So you want to get rid of that di dt part. So you can use the Laplace transforms to do that, and mostly we'd just be using a table. But if you did want to work it out from first principles, it's the integral from 0 to infinity of the function times e to the minus st, where s is the complex Laplace variable. So you've done that as well. We looked at from first principles, and we also looked at the tables. And we looked very briefly at inverse Laplace transforms, so converting back into the time domain. Then system responses you've spent a good time on, because you've done your coursework on that as well. So that was looking at step responses, essentially, peak time, settling time, overshoot, first order systems, second order systems. Yeah, how they respond to a step response. We haven't done the block diagram models bit yet. We'll probably do that next week. That's the last part of the control theory. And today we're going to do the stability and steady state errors, which kind of leads on to your next coursework as well. So I'll also go over your next coursework with you. 5 and 6. Actually, I think they're combined. I don't think that is actually 5 and 6, because I think we... But anyway, root locus techniques and this kind of combined, because root locus techniques is the bit for your coursework anyway. And then frequency analysis techniques was the stuff you did with the Bode plots, Nyquist-Nichols plots. You did a bit on your coursework as well, so that's with the swept frequency. So we've done all that. It's quite a lot. Certainly quite a lot of maths and all that, so you can feel quite pleased with yourselves. So far I've had a look at a few courseworks and they all look quite good. Certainly nobody anywhere near failing, so usually can't fail a coursework unless you don't hand it in, to be honest. But subjects like this are not too bad. There's a lot of that. Right, so I think we'll go on to the steady state error analysis and the bit about stability. We have touched on the bit about stability already. So we talked about poles and zeros. And I think I mentioned to you that poles need to be in the left-hand plane of the closed loop system for the system to be stable. I think I did mention that to you a few weeks ago. Anyway, there's a bit more on that today. So. Is that everybody here now? Yeah. So it might be a bit of a longer lecture today because I'm going to go over the coursework as well. So hopefully that's all right. But, I also going to need my other book. So this relates to chapters 6 and 7 of your book. The coursework's more chapters 8 and 9. But we're not going to go into a huge amount of detail in 8 and 9, so you can combine them a bit. And this isn't too difficult a subject compared to some of the stuff you've done. So you already know this, actually. This is just defining. When you look at your system responses, you know that if the system eventually settles to a steady state value, that system is stable. You know that if the natural response starts to get bigger and bigger and bigger, that's obviously unstable. And they can define marginally stable if you do like what you did with your Ziegler-Nichols ultimate cycle tuning, where you get a constant amplitude sine wave response to a step input. That's a marginally stable system, theoretically. Of course, you would never design a system to be marginally stable. That's bad. So the key thing with the stable systems, if you look at the closed loop poles, if the system is going to end up at a steady state value to a step response, the poles are always on the left-hand side there of the pole zero diagram. So I think I did show you a wee bit about pole zero diagrams. It's just basically a real axis and an imaginary axis, and you plot the position of the poles. We talked about what are the poles again? Can you remember? How do you find the poles of a system? You did this in your coursework, so you should know this. If you've got a transfer function like that, all right, we can't just assume it's an open loop transfer function, never mind about the fact we're looking at closed loop poles. What would be the poles of this system?
-1.
-1?
-2, 0.
And 0, yeah. So the poles are where you set the denominator of the closed loop system to 0 and the values of x that you can pick to make that 0. And they're represented by crosses on the pole 0 diagram. So as you know, you can get real poles. We did do this, I think, already. You can get real poles, which represents an overdamped system. You can get two poles on top of each other, which is critically damped. You can get imaginary poles, usually in pairs. But when you factorize, you can get an imaginary part, and that represents an underdamped system. And the closer the poles move to this axis, the less stable the system is. Okay, so once they get to that axis, that's your critically damped or, not critically damped, sorry, undamped or marginally stable system. Okay, so that's a typical example of an unstable system because of these poles. Okay, there is still a pole on the stable side as well, but these two cause the instability. This is obviously a third order system. It's got three poles, not just two. Okay, so the problem is that you can't always quite easily work out the factors to give you, that's the open loop one, which is fine. But when you come to closing the loop, if you remember, I don't know if I can write on this, but when you close the loop, the equation becomes something like that. If you've got, and this one's got unity feedback actually, so that would just be 1 + 1 + g. But anyway, the equation becomes a bit more complicated, and it's a bit more difficult to find the poles. So there are some other methods we can use to work out if the system's stable or not. And one of them is working out what the steady state error is going to be. I think that's what this is on there. Oh no, sorry, ROUTH-HURWITZ, this first, okay. So one of the other methods is to use this ROUTH-HURWITZ criterion, which is a little bit complicated, but it's a standard table and you just fill in the values and then analyze whether or not your system's stable or not. So this is the equivalent closed loop system being converted to an open loop system. So essentially, if you had G, H, I don't know if we've done this in a lot of detail because this is kind of the block diagram bit, which we haven't really done yet, but that system, as I said, the closed loop equivalent of that is that. So you can represent that same closed loop system by just a single block like that. Yeah, where G is the forward transfer function and H is the feedback or the sensor transfer function. So we're assuming that this has already been done here. So that's essentially the closed loop system, but represented as an open loop block. And then what we're looking for is the multiplying factors of the denominator of the powers of S. So for instance, A4 is the multiplying factor of S to the 4, A3 is the multiplying factor of S to the 3, and so on. Yeah? And then you can fill these into this ROUTH-HURWITZ table just in this way. So for instance, if that was 5S4 plus 2S3, you would put a 5 in here, you would put a 2 in here. You understand that okay? I think that's quite easy. You don't understand that. Okay, let's do an example then. There is an example in a minute, but supposing your denominator was 5S4 plus 3S3 plus S to the 1 plus 7. Yeah, this would be A4, this would be A3, this would be A1, because no A2, so A2 would be 0, and this would be A0. So you just fill these numbers in, so you would end up with 5, that would be 0, because we haven't got one of them, that would be 7, you want to tell me what the rest of them are? A3? 3, yeah. A1? 1, yeah. Good. 0, yeah. Do you understand that now? Yeah. Okay, but that's just the first two rows. Unfortunately, the next two rows get a bit more complicated on the next slide. But anyway, you carry on filling this in. I'll go to the next slide anyway to show you the next two rows. So this looks a little bit complicated, but have you done matrices? Some people have. I'm guessing the guys who were here longer ago maybe haven't. I showed you a wee bit of matrices earlier. This is the... I forgot the name of it now. When you find a matrix, so you can help me out. What's the name of the thing when you cross multiply? I forgot the name of it.
Determinant.
Completely out of my mind.
No.
Maybe it'll be on the next page. No, it's not. I've forgotten. Anybody remember what that's called?
No. Cofactors? No, it's not.
No, it's not the cofactors. It's the next thing after the cofactors, the final thing.
Go on, search it.
I'll check in a minute. I'll check online. I'll remember as soon as I see it. I can tell you how to get it. I just can't remember what it's called. Might be the determinant.
But the determinant is not one.
I think it's the determinant.
Is it?
Determinant. Yeah, it's the determinant.
Well done, Robert.
I forgot the name.
Yes, Robert.
What was that?
Robert said that.
Did he?
Yeah.
Oh, well done, Rob. You should have said it a bit louder, didn't you? No, good. Right, yeah, the determinant of the matrix, which I completely forgot. I should have known because I was doing matrices yesterday, but there we go. Yeah, so this top line is the determinant, and you can find that with a 2 by 2 matrix. You just multiply... Oh, it's not letting me rub that out now. Never mind. Multiply A4 times A1 minus A2 times A3. Write that down. So for that one there, the determinant would be A4 and A1 minus A2 times A3. That gives you the determinant, which is what those lines are representing. Yeah? And of course A4, A2, A3, A1 are the numbers you filled in on the first two rows. Okay, then you've got a negative sign. There's an example later on. Then you've got a negative sign, and you divide by A3, which is the multiplying factor of S to the power of 3, and so on. And you just do that for all of them. Some of them work out quite easily, because obviously this one's going to work out as 0, that's going to work out as 0 as well. Now, I don't know the maths behind how the equations appear in the table like this. The guy Ruth or Hurwitz, or the pair of them, obviously worked that out between them somehow. I don't know how. Better mathematicians than me, but you just need to have the table and then fill in the parts. And by the way, you'd never be expected to remember this. If you were asked a question like this in an exam, you would be given the table. but you would be expected to know how to fill in the numbers on that table and how to do the determinants part. Okay, so if we carry on, I think there's an example here. Okay, so we're not going to go into how you get from there to there at this point. I think I did show you that, but it's that g over 1 plus g equation. In fact, it's quite easy for a unity feedback because when you multiply that out, you get a single number by itself, and then you just add it to the top line. That's a kind of trick way of doing it, but in fact it is g over 1 plus g. So equivalent closed loop transfer function is this here. So we've got a factor of 1 for A3, 10 for A2, 31 for A1, and 1030 for A0. So this is an example of ROUTH-HURWITZ. I haven't actually explained how it works yet, but you'll see on the next slide, I think. So we can fill that in. That's just filling in the numbers as they go. I think that was A3. Yeah, A1, and so on. Yeah, just as per the table originally. This one has a common factor of 10, so you can actually make the maths a little bit easier by dividing. You don't have to do that. If you forget to do that, it wouldn't really matter. Just mean you're multiplying bigger numbers, that's all. But you can see that dividing by 10 just gives you that. And then you work out your determinants and change the sign and divide as per the table as well. So we've got 1 times 103 minus 1 times 31 gives us 72. Change the sign, divide by 1 gives us minus 72. And so on. This one obviously gives us 0. This one would be 1 times 0. 103 times 72 minus 103 times 72, which makes it positive. Divided by minus 72 makes it minus 103. Times the minus sign gives us 103. And so on. You can have a look at that yourselves. I'm sure you'll figure that out. If you can remember how to work out determinants. Okay, then the key thing is, if there's no sign change in this column, the system's stable. And if there is a sign change, the system's unstable. So all this maths is only just to look at the signs in this column. Okay?
Sorry.
It's a lot of maths for a very simple check. So by sign change, I mean if any of the numbers go from, if one of the numbers is positive and another number is negative, then that means the system's unstable. So with this system, would this be stable or unstable?
Unstable.
Unstable, yeah, because we've got 2 positive numbers here and 1 negative number here. That's all this whole thing does. It's complicated maths for not very much gain, if you ask me. But okay, the systems of higher order, or with imaginary poles, can't really be worked out this way, but it's fine because what you're doing is just going to be systems with real poles. So you can have a go. I'm sure there'll be some examples or practices for you to try further on. So here's another example. That's the open loop system for transfer function. So we've got one there. So I think that should work out as 206 as the last number. That doesn't actually look right. Oh no, because it's 6s. Sorry, yes, it will just be 200 because that's 6 times s. Yeah, that's right enough then. And again, filling it all in. A4 is 1, A1 is 11, sorry, A2 is 11, A0 is 200, A3 is 6, A1 is 6, and so on. And you can see here again, because there's negative sign change, that's an unstable system. But this is the sort of thing you've really got to practice. There's no point me just talking about it, because you have to actually do it, yeah. Okay, then you can also work backwards. You can use the ROUTH-HURWITZ table to determine the system gain, kind of similar to when we looked at gain margin and phase margin with our boat plots. Remember I said if you add so much gain, the system becomes unstable. So you can work out how much gain you could add without having a problem. You can do the same with ROUTH-HURWITZ. If you have a system, and this is obviously a gain term on the top line here, because remember gain is just a multiplying factor. So the system is obviously 1 over s plus s7 s plus 11, and then we're multiplying by a value k, which is a multiplying factor or gain. And we can work out the value of k just by doing exactly the same thing using the ROUTH-HURWITZ table. So if you multiply that out with your g over 1 plus gh, you end up with this formula here. So you can see k is now ended up on the bottom line. So it's going to become part of our table. Yeah? So filling in the table, as we're used to, you end up with this. You can't obviously work out the determinant directly because you've got this k value which is going to vary. You're trying to work out what k value is the best k value to use for the system. So it's going to vary, so you end up with an equation instead of a single number. But you can see here that these are all positive. Well, k is probably going to be positive. It's unlikely you're going to have negative gain. I don't think you're going to have negative gain. So the only one that's likely to be negative is this middle one. This 1386 minus k over 18. That's the only one that could possibly have a sign change in that column. So all you need to do is work out what value of k would make that 0, and that would be the maximum value of k you could have before the equation became negative. Yeah, so obviously the top line is 1386 minus k. It's quite straightforward. It's obviously 1386. Yeah, if k is any bigger than 1386, that becomes negative. Does that make sense? Yeah. Okay. Good. I think that's just what it says here. Yeah. So you could have gain of up to 1386. Obviously, you wouldn't really in the real system, because you've always got to allow for factors of safety for environment and changes. But theoretically, you could have 1386. Okay, that's really the end of the ROUTH-HURWITZ bit, which is kind of a bit separate from the steady state analysis, but it's just another. It introduces you to poles and zeros and Argon diagrams or pole zero diagrams. But the next bit we're going to go on to is steady state errors, which is like a subject in its own right. So it's like a completely different subject. Okay, I'll give you a few minutes to take that in. It's quite hard jumping from one thing to another. Not very sure why I put them both together, but there we go. Okay, so we've got different inputs we can input to a system. I've talked about this already. You've got your step input, which is a sudden change from one position to a different position for most things, yeah? From one value to a different value, like an elevator going maybe from floor 0 to floor 4 or something like that. So that's quite useful for working out the transient response, i.e. and what's going to happen as the system's changing. And it also, because it's a step, it'll also give you the steady state response as well. But to be honest, a ramp input is a better indicator of the steady state response because you don't have to wait ages for the system to settle with a ramp. You can see straight away what the steady state error is going to be. I'll demonstrate that a little bit later on. Parabolic ones we're not really going to be looking at, but they represent a constant acceleration. We're not going to really do them, so we can leave that then. Oh yeah, ramps represent constant velocity. Yeah, because they have a constant slope, rate of change. Steps represent constant positions. So once you've had your step, that's the position set. It's not going to change. Okay? But ramps, obviously, the position is changing with each time step. But the speed or velocity isn't changing. It's the slope. Right, let's just leave it there. You've seen this already. So that's obviously step, ramp and parabola, and that's the Laplace transform of those equivalent inputs. Yeah. That's just done by just doing. I think I did show you this. I'm not going to do it, but that's just by doing that equation. Gives you that. Okay. Which is the Laplace transform equation. And by the way, you need to be able to do these sort of things for the exam, or possibly you need to be able to do these sort of things for the exam. Not for the parabola, but certainly for the first two. Okay, so we know the steady state error. This is a formal definition. It's the difference between the input and output for a prescribed type of input, yeah, so whether it's a step or a ramp or whatever, as the time tends to infinity. So you're going to see this little infinity sign popping up quite a lot. But that's just to say that you can only measure your steady state error once the system's completely stopped changing and settled down. So obviously if you measured it at time infinity, You can't get any longer than that. So if it hasn't settled down by then you're not going to get steady state error measurement. So that's all that means. It just means that measure it after a very, very long time. Not before that. I did notice one or two people in their coursework, I don't think there was anybody here, it might be one of the remote students, had just simulated their system for 200 seconds and it was still doing that, and then they got the top of one of those bumps and said, oh, that's the steady state error. But of course that's not the steady state error because it's still changing, it's not steady. You can measure steady state error when it's not changing anymore. Okay, so this stuff should be more or less revisioned for you. If that's the reference input, and output 1 is reaching that reference input, it's obviously got 0 steady state error. Just getting to what we want it to get to. And output 2 has obviously got an error, which in this case has been represented by E2 at time infinity. That's what that means there, E2 at time infinity. So E2 is the amplitude, and the infinity is just the time it's measured. And then if you look at a ramp, you can see that output 1 is this line here. It's a wee bit difficult to see, actually. This line here, I'm going to do this wrong, I suspect. Okay, so if you look at output 1, after a long period of time, effectively infinity, there's no error there. You can see that. Yeah, output 2. So the input's a ramp. It's this top line at the top here, yeah? The input's this line here. So that's the input, yeah? So output 2, I hope you can see output 2's got the same slope, but just continuing. So that one's got a constant steady state error. So that would always have the same steady state error. When that system has settled, there'll always be a specific error, and it's not going to change. So that's output 2. And then output 3, if you were to measure that at infinity, it's getting wider and wider and wider. That baby shark. Wider and wider and wider. I don't know why I was watching that the other night. Anyway, there we go. At infinity, that's going to have an infinite error, yeah? I'll run you off anyway. Okay, does that make sense?
Yeah. After your good explanation, it makes perfect sense.
Right. So there is a little bit of a derivation for the theory behind this steady state error calculation, yeah? And it's based on your standard closed loop model with your feedback, with unity feedback, okay, so with no h of s function. So this is something you probably need to learn. I'm not sure if it's in the exam or not, again, but it's something you need to possibly know. So you just analyse each point in turn. So starting with this point E here, because we've got unity feedback, the whole of this signal is being fed back, essentially. Yeah, so you've got C of S there. Never mind the brackets S, that's just to say it's in the Laplace domain. So you can see here, this is a subtraction block, so E is going to be R minus C, which gives us this first equation. Yeah, R going into the subtraction block, C going into the minus part. So the output is going to be R minus C, and E stands for error. I think I did talk about this. I'm trying to remember if it was with you or with the Chinese people. Error, that's the error. If you remember with your PID controller works on the error to try and remove it. So, right, what else do we have? We've got at the output here, simple multiplication. This is going into the transfer function. That's the transfer function, so that output is equal to the error times the transfer function for this particular diagram, which only has the single transfer function. So we can do some substitution. We can substitute this into that point to give us this equation. You still following that okay? Yeah, just a little bit of algebra. And then we can do some rearranging. So take all the E's, all the things with an E in them to one side and leave the others on the other side. So essentially, change colour. Essentially taking this term over to this side. Yeah, so it becomes positive, that's your normal algebra. basically adding it to both sides. So let's just do that as one more step. You see that I've kind of jumped a step there. So what you'd have is E of S plus E of S times G of S equals R of S. Yeah, that's just another step. Going from there. Is that okay? Well, just algebra. Should be able to do that. Okay, then we can take out the E because it's common to that term and that term. So that's it taken out of the bracket. Yeah, and you're left with 1 plus G of S, because 1 times E of S gives you E of S, and obviously E of S times G of S gives you that. And then just with a little bit of rearranging, cross-multiplying, dividing, whatever you want to call it, we end up with a equation for the error, which is essentially your steady-state error. Yeah? So this is the equation for your steady-state error. The error equals the reference divided by 1 plus the transfer function. Now, is that okay? I don't want to go too fast. People follow the algebra okay on that? Yeah? Yeah, good. Okay, some people are nodding. As long as some are nodding, that's probably all right. Now, there is a maths final value theorem. I don't think you'll have probably come across this before, which says that, it's essentially this. If you're looking at the limit of a function as time tends to infinity, in the Laplace domain, that translates to a function s times the same function in the Laplace domain as s turns to 0. So 2 things to note there. The time was tending to infinity, the s becomes tending to 0, and you've got this s multiplier term. Okay, so it's not just a straightforward transform E of t to E of s. There's also this little s term. So I guess that's the two important bits that are different. Okay, and then s times E of s obviously just becomes, if that's E of s, you just substitute that in. So that's this bit. That's the E of s part, the error part. And then you've got the s multiplier, which is that. From there. Okay? There's actually an easier way of working this out anyway, but sometimes in an exam you get asked both ways, so you do need to know both. But I'll show you the easier way too. So you can obviously work out what your error is at at infinity, or essentially a steady state error, which is this term here, by using that equation in the S domain. R's your reference to use your transfer function, remember. Okay? That's rather a lot of maths for a Tuesday morning. Okay, so for instance, if you have a step input, we already looked at the Laplace transform of a step input, which gave us 1 over s. Yeah? And again, that's just from doing your function of e to the minus st dt, where in this case f of t equals 1. That's a unity step, yeah? Obviously, if it was a step of 5, f of t would be 5. If it was a step of 10, f of t would be 10. Yeah, 1's just for a unity step. But this is talking about a unity step, looking at that there. So if we put that into our equation, using our final value theorem, and we end up with that the error, steady state error at infinity, is equal to the limit as s tends to 0 of s, which was this s here, times r, which is 1 over s, times over 1 plus g of s, yeah? So not too much to worry about. It's easier to work out with an actual example. Okay, and yeah, so the s's cancel out. Yeah, s divided by s just gives you 1, so that just becomes 1 on the top line. So that bit just becomes 1 on the top line. This bit obviously is going to stay as 1, regardless of what value of s you have. Yeah, s could be 500, that will still be 1, that will always be 1, that's a constant. So that's where that 1 comes from. So the only thing that's going to change as s goes to 0 is this g function, yeah? As you can see, that's going to be different. for different values of s. If you skip back to an example, where do we have an example? Somewhere. Yeah, so for instance, here's a sort of G-type function. You can see here, if you made S0 here, that's going to look different, isn't it? That's going to look like K over K. Yeah, because that would be 0, that would be 0, and that would be 0. So the only thing that changes with S changing is the G part, yeah? A bit blind, but I think when I show you an example, it'll make more sense. Okay, and that's called the DC gain of the system. Again, you don't really need to worry about that. Okay, so you already know that the only way to remove steady-state error completely is to put an integrator into the system. And you've already seen on Simulink that the integrator is a block that's got a 1 over s. I think most people will have come across that at some point. Maybe, maybe not, but anyway, believe me, an integrator, the Laplace transform on an integrator is 1 over s. So if you have an integrator in the system, you're going to have a phi s term in the denominator, because you're going to have a 1 over s term somewhere in the system. That's the only time you'll get an error of 0. And that's all that next bit's saying anyway. And that's just from our PID theory. We know that if you put an integrator in our PID theory, our steady-state error disappears. I think most people did find that when they did their coursework. And then we got confirmed. Was the last one a ramp? Sorry, that was for a ramp. I missed that one. So the only difference here is we're putting in a ramp, which a unity slope ramp. So when I say a unity slope ramp, that's a ramp that's going up for each one step in time. It's going up by 1 amplitude, whatever it is you're measuring, whether it's level or flow or whatever. So for a ramp with a unity slope, the Laplace transform of that's 1 over s squared. So you can see here that you actually end up with 1 over s on the top line. So essentially what you'd end up with is 1 over s over 1 plus 2 over s. And of course 1 over s on the top line is the same as multiplying the bottom line by s. It's like just multiplying 1 over s times 1 over 1 plus g over s. So you end up with this equation here. So again, if we make s 0, obviously that's going to disappear because that becomes 0. So all you're really looking at is what happens to this transfer function multiplied by that s as s becomes 0, which might not necessarily be 0, okay? Because imagine that your transfer function is 1 over, I don't know, say it was 1 over s, say that was your g of s. Yeah, you multiply by that s by s, you're going to get 1. Even if s is 0, it doesn't really matter what s is, you're always going to get 1. So it's not necessarily going to be 0, even though that s is 0. Okay? So for a parabola, sorry, for a ramp, if you've got no integrators in the forward path, you're going to get an infinite error. Okay, so if there's no integrators in the system, you'll get an infinite error to a ramp input. If there's one integrator, then you get a finite error, so an error that just stays the same, no matter how long you leave the system running for. And if you've got 2 integrators, you get an error of 0. I don't think I went through that with the other one, but so if there's no integrators for this one, you get a fixed error for a step. If there's one integrator, you get 0. You know that already. Okay, so. And then the last one's the parabola. I said we're not really going to look at that, but there is an example there. Unity parabola is 1 over s cubed. So you end up with this s squared term on the bottom line instead of the s term, or the no s. And then, so the difference with if you apply a parabola to your system and there's no integrators or one integrator on the forward path, you'll get an infinite error. If there's 2 integrators, you'll get a fixed error. And if there's 3 integrators, you'll get no error. So you can kind of see a pattern emerging, yeah? The higher the order of the input in terms of s, the more integrators you need to remove the error. make the error 0. I wouldn't worry too much about that anyway. But so there's some examples here. Find the steady state errors of this system to a step input of 5. So when I say that 5 UT represents a step that's going from 0 to 5 at time 0. And then a round, what do you think that round would be then? If I go across one time step, what amplitude will that round be at? If it's represented by this function here. Will it be 1?
Five.
Yeah, it'd be 5. Well, it'd be a trick question. There was a lot of blank looks. I thought you would have got that. That could be. Yeah. So that's a ramp with slope 5, essentially. Quite right. Good. Okay. I think sometimes maybe the way I ask the questions, you don't understand what I'm talking about. But never mind. Okay, so that's what we're looking at. We're looking at what's the steady state error for those two different kinds of inputs. So we can do it with this final value theorem. There is an easier way, which I'll show you in a minute, but we can do it with this final value theorem. So what was this transfer function that? Trying to work out 3 plus 12. Yeah, so we're looking at the open loop transfer function. I was just trying to figure out why. But this G of S is the open loop transfer function. Going right back to the first slide I showed you on this stuff. Yeah, where we said the system was a system with a G in unity feedback, yeah? That's the same as this system here. A G of S and unity feedback. So we're only looking at the G of S. We're not transforming that to the closed loop equivalent. And then we're just going to use our final value theorem, where for a step, 120S plus 240 was the top line. Okay, so we're not looking at the step yet. We're just looking, first of all, at the limit as S tends to 0 of the transfer function. That's because, way back here, not that one, this one. The thing we're interested in mostly is this bit. What happens to that as S tends to 0? And then we can substitute that into the equation to get the full value. So basically, you've got your equation. You have this straightforward G of S equation. You put S equals 0 into that equation. So that 120S term is going to disappear. That's going to disappear, that's going to disappear, and you're just left with this part, yeah? Which then gives us this 20. But of course, that wasn't the full equation for final value. The full equation for final value was R of S over 1 plus G. S times R of S over 1 plus the limit of G of S. So all we found out so far is just this value. So putting the rest of the numbers in, this bit here, this 5, that's the R part, and that was the S that came about by the final value theorem, S times the G of S. So that cancels out to give us 5, which is that top line. So we've got 5 over 21, which gives us a final answer of 0.238. Okay, so that's saying if you put a step of 0 to 5 into this particular system, you're going to get, I don't know what it's going to do, but your error at the end is going to stay constant, and it's going to be a positive value. It's just going to stay like that forever, 0.238. So that's telling you what your steady state error is. That's the whole point of this. Okay, and you can do the same thing, just a different input this time. So this time, because it's a ramp input, we've got this extra S term here. Yeah. So that obviously is going to become 0, so we end up with 1 over 0, which means we've got an infinite error for a ramp. So essentially, if we put our ramp in, our output's going to do that. Yeah. And the error at time infinity will be infinite. Okay. Well, you've probably noticed that the number of S terms that you're multiplying by is equivalent to the system type. Does that make sense? No, that doesn't make sense. I'll just explain what I'm talking about there. You can classify the system in terms of its steady-state error response as a type of system. And it depends on the number of S terms in the bottom line, in the denominator. Because we know straight away, if there's a single S term here, then the steady-state error for that is going to be what? If you put a step into there, what's the steady-state error going to be? This is like an integrator. 1 over S is an integrator. So what's your steady-state error going to be? 0. Yeah, I've told you that already. That's like adding an I term, yeah? An integral at a time. So you know that if you put a step into a system with an integrator, steady state error is going to be 0. That's the whole point of adding pi, the I part of the PID. Yeah? So you can classify the systems in terms of the number of S's in the denominator. Now that's not the power of S's. It's the number of individual S's that are on their own. So for the first system, although you've got this S squared term, this is still a type 0 system because there's no independent S. The S is part of the whole equation, yeah? So that's a type 0. This is a type 1 because it's got this S term here by itself, which essentially represents an integrator. And this is a type 2 because it's got this S squared term by itself. Okay, in fact, every type of system reacts in the same way to the same kind of input. So, for instance, all type 1 systems will always give you 0 steady state error to a step. Yeah? All type 2 systems will always give you 0 steady state error to a ramp input, and so on. Yeah? So there's a kind of a table. That's just, I thought I would have asked you this, but anyway, that's just a wee example of the different types. Here, although there's S's there's nothing when you multiply that out, there's no S's by themselves, so that's a type 0. This one's got the S here, so that's type 1. That's got an S cubed, so that would be a type 3. Okay, looking at this one, what type of system do you think that would be? 0. Very obviously 0. There's no S's on the bottom line. Yeah, good. Okay. That's fine. You didn't even really need to do the multiplication for that. That's straightforward. Okay, so we can specify some things that are based on the system types and the type of input that we're thinking about when we're trying to analyse the steady-state error. There's essentially 3 different inputs and 3 different constants that are related to those inputs. So I already said a step is really a change in position from one position to another. So we've got a thing called a position constant, which is related to a step, and which is actually defined as the limit as s tends to 0 of our transfer function. And then we've got velocity constant, which is related to a ramp input, which I said was a constant velocity change here. So that's just got this extra little s value in it here. And then we've also got the one for the acceleration constant, which was the parabola, which has the s squared term. But they're essentially very similar. The 3 equations are very similar. That's the 3 constants. And we can use these constants as a kind of easy way of working out the steady-state error rather than going through the full final value theorem. It actually is very closely related to the final value theorem, but it's a slightly easier way of doing it. So as it turns out, you can have this sort of table where, okay, for your 3 different inputs, step, ramp, parabola, the actual steady-state error can be calculated from those constants. Okay? So the way to calculate the steady-state error for a step is always to use this 1 over 1 plus the position constant. And the other 2 are a wee bit easier. The way to calculate steady-state error for a ramp is 1 over the velocity constant. And the way to calculate the steady-state error for a parabola is 1 over the acceleration constant. And of course, they can be worked out using these equations. So the way you would do it, you would work these out first, and then put them into these equations, and that would tell you a steady state error for the different types of inputs. The table's just summarising the answers you would be likely to get if you did that, or the answers you would get if you did that. So for a type 0 system, which is all this column here, this first column, your steady state, sorry, your position constant will always be a number, a whole number, yeah? Or not a whole number, it could be a fraction, but it'll always be an unchanging number, a constant number. And your error will always be worked out by that. And it works out that gives you a constant error. Yeah? That's for type 0, because remember type 0 doesn't have any free S terms on the bottom, so it's like not having an integrator. So you have a constant error. What I mean by that is fraction input. Constant error. Yeah? Log that out. It doesn't apply to the other two. And your error for a ramp input is always going to be infinite, and your error for a parabola is always going to be infinite. So that's for a type 0 system with no free S's in the bottom line of the transfer function. And then you can do the same idea for the type 1 system. What you find out there is your error is always 0, which is what you'd expect because you've got one free S term in the bottom. So with a step input, your error is always 0. With a a ramp input, your error is 1 over the velocity constant. So that's a constant error that doesn't change. So that's like when you had the two ramps. You put your ramp in there. Constant error, yeah, not changing. The difference between the two ramps isn't changing. So that defines by that. And then your error for a parabolic input would always be an infinite error. And then finally you've got your type 3, which has 0 error for a step, 0 error for a ramp, and a constant error for a parabola. Yeah, does that make sense? Hopefully. It's not too bad. And you can always work these out, of course. You don't have to remember the table, but the table is just a useful way of summarising what's going on. And there is a kind of relationship between the three systems and the three inputs as well. Okay, it's a bit mathematical, I know, it's probably quite tough. But... Okay, so there's an example. We could just do the example, I guess, together. Probably the easiest way. Now, the wee thing, especially when you're doing the exam, guys, is make sure you take note of the size of the steps and the size of the parabolas. Don't just always assume it's 1. In this example, each one's 5. I'm not sure what a parabola of 5 is, but certainly that's a ramp that's got a slope of 5, and that's a step that's got an amplitude of 5. Okay, so we're only really going to be looking at the G of S values here. So the G of S, if you multiply it out, I think that's the same as the last example actually. We've got 120S plus 240, that's just multiplying the top line. And the bottom line is S squared plus 7S plus 12. Yeah? So we can start by finding our position constant, which is the limit as S tends to 0 of G of S. Yeah? So that's the KP value, that's the first thing we could find out for our step input. So the actual step hasn't come into it at this point, we're just working out the position constant. And by making all the S's 0, and working out what we have left, which is the 240 over 12, which gives us 20. And then we have a much simpler equation than we had with the final value theorem. We just need to put that into the equation, input divided by 1 plus kp. So the input was 5, amplitude of 5, that's where this 5 comes from. 1 plus kp is going to give us 21, 20 plus 1. And that will define our error. There'll always be a 5 over 21th error between what step you put in and what output you get out. For a ramp of 5, obviously if it's a ramp, for a step of 5, a step of 1 or 2 it'll be different. And then you can do the same thing for kV and ka, but we already know from the table that they're both going to give us 0, because there's no free S on the bottom line, so this, if you multiply by 0, you get 0. multiply by 0 squared, you get 0 as well. So they're both going to give us infinite errors, because it's always input over constant, input over constant, where the constants in this term are 0. Okay, so that's one system. That's it. I think that's the answer. It's quite an easy exam question, that, actually. Don't know how many marks it would be worth, but it's quite easy to do. Right, that's the end of that bit. Any questions? I did that quite quickly, and I'm kind of aware of it.
Can you move up, please? One slide.
Yeah.
How you can solve 120s over s squared plus 7s to get rid of them and end up with 240 over 20?
Yeah,
12.
Yeah, you're not solving them.
You're not solving.
What you're doing is you're looking at the limit of this equation as the s tends to 0. So the best way to do that is to make all the s's become 0 in the equation.
Oh, yes, I'm going to play. Right.
Okay, so that will become 0, because that will be 120 times 0. This will become 0, because 0 squared is 0.
I skip that.
Yeah, you got that, yeah.
Yep.
Okay, so that's all you're doing. I know it says limit as s tends to 0, but what you just do is you just make s equal 0.
Right.
And then just calculate it from there. Okay, what I was going to do with you next was the coursework, which is also quite mathematical, I'm afraid. The coursework, I've given you the program, the MATLAB program, so all you need to do is edit it. So you don't have to actually understand the theory in a lot of depth.
Should you just edit the program?
What's that?
Should I just edit the program?
I'm not giving you the edit wrong, you'll watch the different one. So I think I'll go through the coursework now, is that all right?
Yeah.
Because you can all get started on that. That's too nice. Okay. So your deadline this time is the 7th of December. Okay, well I don't know how long away that is. What's that, about a month away? Well, a wee bit more than a month actually. So that's quite a long time.
We'll get an extra week in that, will we? Because we had an extra week in coursework one.
Sorry?
We're working coursework one for an extra week. The extra week good.
No, I can't put that back because that's on the last week of term, I think. It might even be the week after the last week of term, I'm not sure. Anyway, so yeah, so you start with that date. Your last coursework, you looked at PID controllers and you looked at tuning them. This is a more exact method of tuning, but it's very mathematical. That's the only thing I would say. It's a thing called the root locus method of tuning and adding a compensator. So adding essentially poles and zeros to your system to get the response you want. And we're going to do it all in MATLAB. You don't have to do anything by hand. Right, okay, I'll just go on to it anyway. So this one's worth 20%. The last one was 30%, which makes up your total 50% marks. And then the other 50% is your exam. So this is called a cascade compensator. And what they mean by that is you can actually tune the response of your system by adding additional components, cascading them together. There's various different things. You can add lead compensators, you can add lag compensators, lead lag. We're actually going to design a PID one, which is a proportional lead and lag type one. Got everything in it. But the MATLAB file essentially does it for you. You've just got to understand what the MATLAB file is doing and be able to change the numbers to suit your system. So the way it works is, I'll talk about this in a minute actually, but I'll just show you what we're doing. So first of all, you need to know what your name is, your surname. I think most people are okay with that. And you pick the letter from your surname. No, this is just so that I don't have 120 courseworks all exactly the same or more. So you pick the letter of your surname, and this will be your open loop transfer function. Okay? So essentially, it's going to be an open loop system related to your name, and we're going to add feedback to that, unity feedback, and a PID controller. If I can draw on here, it would help. So you've seen the systems quite a lot. So we're going to have, oh, that's not me, let me draw. Okay, so that's the system that's defined in the coursework spec, yeah? What you're going to add, but this time using MATLAB, not Simulink, is, I did that wrong, didn't I? Controller. Let's draw this further across. It's actually done in that order. So it's still a PID controller, but it's done. First you do the proportional part, then you do the derivative part, then you do the integral part. And the reason for that is, I think I told you, PID controllers are quite complex, quite expensive. So if you can get away and achieve your spec with just a proportional controller, then why bother with the ID part? You don't need to bother. In your case, you're obviously going to need the I part because the steady state error is always 0. But not always. You wouldn't always need that. So essentially what you're going to do is add all that to your open loop system and tune it, using this root locus method. Okay, so this is your open loop system. You can see that you wouldn't be able to do this easily by hand because they're all third order systems. So we haven't even looked at third order systems, but it's to demonstrate how this tuning process could really work for any system. It doesn't need to be a second or first order system. And then we've got some specs. So last time the best response you could get was a quarter amplitude response. The Ziegler-Nichols methods always give you quarter amplitude response. This method you can actually tune to a particular specification. So this is obviously with a step input, a unity step input. And we're looking for these different values depending on which row you're on. But a specific percentage overshoot, a specific peak time. If you remember, peak time is the time. Oh, peak time, that's not what I'm trying to do. So, peak time is going to do something like that. So this time here, from 0 to there, that's your peak time. So we're looking for essentially a rise time, but peak time is easier to measure. So a fast response and 0 steady state error, I think was the last bit, which means you need an integral controller. Okay, if you've got the book, I think most people do have the book, the niche book. This very closely follows the example in chapter 9, 9.5. So hopefully you'll have that. Let's scroll down. And essentially your aim is to achieve a system that meets that spec. But I'll show you how to do it. I'll run the file and show you how we're doing it. I need to explain a wee bit about root locus plots first. So I'll pop that onto there. I don't think he's very good. Okay, so if you have a system like that, what you end up with is, on the denominator, you end up with a 1 plus k times g. In fact, if you had an h, it would be 1 times k gh, yeah? So what we're interested in is plotting the poles of that system where k is a variable. K is a variable gain, variable from 0 to infinity, essentially. Because if we can do that, we can choose a specific value of k that will make our system stable. So k would be like a proportional controller, to be honest. But we can choose a value of k to give us a specific response. So what we actually do is plot the poles of that system, which is the closed loop system, essentially, because it's the denominator. If we were to put that into a closed loop, what we'd have would be k, g, s over 1 plus k of s. And as you know, the poles are related to the denominator of your system, yeah? Everybody knows that. So if we wanted to plot the closed loop poles of the system, we could plot the values of 1 plus kgs. as k varied, and that would give us all the possible poles for all the different values of k. Now, in fact, we actually don't need to bother with the 1 because it's just a small number. It doesn't really come into it much. So what we're actually going to plot is the poles of kgs, yeah? And we can do that on our root locus plot. So if we vary k in tiny, tiny increments, you know, like 0, 0.001, 0.002, 0.003, and what we'll find is that we'll get a kind of picture of the poles as they move, yeah? So, you know, I don't know, you might start off with the poles maybe here, and they might move along as you're changing the value of k, and then maybe they'll split up. Of course, if they split up, they go both ways. So this is just different values of k, you know, k increasing. And you can get MATLAB to do that for you. And of course, if you do it with MATLAB, you don't see the individual poles. All you see is a nice kind of line that maybe does something like that. So that's what a root locus plot is. It's the poles of this KGS. That's called a root locus. Now, the other thing that's quite interesting with the root locus plot is you can add some diagonal lines to that, and they're actually lines of constant damping. Yeah, so probably do a different color. Again, we'll get MATLAB to do this, and I'll show you how it works. But you can add these lines, and each line would be a value of zeta. If you remember your equation for your second order system, just thinking of second order systems, k omega n squared over s squared plus 2 theta omega n s plus omega n squared. Right, hopefully you can remember what all those terms are. K gain, what's omega n? No? No, wrong, too long ago. Maybe.
No, that's the frequency.
Yeah, frequency, natural frequency, yeah. So undamped frequency, essentially. Zeta is your damping factor or damping ratio, this zeta value. And that zeta value is very closely related to the overshoot of your system. Again, quick. I'm not very good at drawing this, but... What you see is kind of something like that for different zeta values, yeah? So zeta is very closely related to the overshoot, yeah? That's not a very good plot. Ignore that just now, we'll come back to that. But anyway, so those lines are lines of constant zeta, which means they're also lines of constant overshoot. Yeah? So if you wanted, say, a 5% overshoot, you might be following that line. If you wanted a 10% overshoot, you might be following this line, and so on. Actually, it's the other way around, I think. The closer you get to the origin, the bigger the overshoot. So that might be your 10% line. This might be your 5% overshoot line, and so on. But they also relate to a particular zeta value. And there is an equation that relates them in the book. I don't know if I showed you that already. Did I show you that? No, I haven't showed you that. Okay, it's also in the MATLAB file anyway. So what you can do is if you have an overshoot spec, you can work out what value of k you need to achieve that overshoot spec by plotting your root locus, which remember is the poles of all the different values as k changes, and seeing where that crosses your overshoot spec line, essentially. So if your overshoot spec was 10%, you could put a pole here, and you would know that that system would meet that spec. Yeah, you could pick a value of k, or essentially proportional gain, that would put your system's pole there, and your pole would exactly meet that spec. It would have an overshoot of exactly 10%. We also know that it's possible to put a pole there because we've already plotted root locus of all the different poles. You want me to wait till you come back? You want me to wait till you come back?
No.
You
Because-
sure? Okay. Right, okay. Maybe show you the MATLAB file now then. So ideally, the first part of it is quite easy. The first part is essentially doing this, plotting the root locus of kg and the lines of constant damping, or your particular line of constant damping for your system, and putting your pole there, and then working out the value of k, and then putting the whole system into a closed loop and seeing what the step response looks like. You will find that that won't actually meet the full spec. That should meet the overshoot spec, but it won't meet the steady state error or the peak time spec, which is why you need the I and the D parts as well. But this is essentially the P design, is just doing this. Okay, I think it's probably best if I go to the file now. Are there any questions? I don't understand that so far. Either you don't understand it at all, or
Seems straightforward enough, it was. Seems straightforward enough.
seems straightforward enough. Okay, it's quite, the theory to this I know is quite difficult. So I should have MATLAB running somewhere.
Just to get it done.
Yeah.
Okay, so this is the program I have given you guys. And I put a lot of comments in here. So all the stuff in green is comments designed to help you do this coursework. And I would be expecting you to change the comments to suit your own coursework. Okay, not extensively, but certainly the values. So I'll just repeat that. I would expect you to change the comments. Okay, I don't want to see people handing in coursework that's saying my open loop transfer function is that transfer function, because that isn't going to be your transfer function. Your one's going to be the one that's defined here. Okay, and so on throughout the thing. Right, you've got your page, your book page numbers. You can follow this example through the book as well. Yeah, hold on. It's quite cold. Give you away anyway. You can follow the example through the book. So in the book, the spec's a little bit different from yours. The spec's for a 20% overshoot, a steady state error of 0, which is similar to what you've got. But in this case, it's asking for a peak time which is points or 2/3 of the open loop peak time. Now you don't have anything like that. You've just got a specified peak time. So anywhere you go, you see this 0.667 times TP, you won't be doing that. Okay, you'll just be putting a number in there instead. So if we switch back here, you'll see you've got peak time of 0.1, for instance, if your surname begins with B.
That's me.
That's you, is it? Yeah. Okay. So that's just a number. It's not 0.667 times that number. It's nothing complicated like that. It's just a pure number. So the file might be a wee bit confusing from that point of view, in that it follows the book design very closely. It doesn't just use a number there, but we'll figure that out. And it's split up, as I said. You start with the proportional controller design, first of all. I'll probably sit down and work these out. So the first thing we need to do is work out the zeta value. You can use MATLAB to do that. I obviously just did that with a calculator. And it comes from an equation in the book, which I'll write on the board for you just now anyway. Chapter 4 page. It's quite a complicated equation, but right, here we go. So anybody who's got the book will have this anyway, but I'll write it here just in case you haven't got the book handy. Probably wrong that one. So if you want to be clever and get a few extra marks, you can write a little equation in MATLAB to do this for you, or you can just do it with a calculator. Maybe to no. What's happened to my board? I'll explain what it's meaning in a minute. I'll write it down first. You can copy it as well. sure I get it right first. Log square.
Should say the green.
Okay. So this is the way you convert from overshoot percentage to dumping factor. So there's a direct relationship between them. But you do need to do this to get that zeta value. So that ln, that's the natural log. So on your calculators, you should have a button for natural log as well as one for log. Yes, it's that we think most people think says in on the right-hand side there. That's actually a natural log button. Log to the base 2. I think it's base 2. Or is it log to the base 2? I'm not sure anyway. It's the natural log. Okay, overshoot is your overshoot in percentage terms, so maybe 2%, 5%. If it's 5%, you would put a 5 in that number there. And obviously dividing by 100 gets it to a fraction rather than a percentage. That's just pi, 3.14 or whatever it is. This bit here, you work out the log first and then square it. That's what that means. Okay, so they normally write that with the square here so that you know it's not the number squared. It's the log squared, the log of the number squared. That's obviously a square root sign. And when you do all that, you should get your value of damping factor. And you should always get a value less than 1, because I think all your systems should be underdamped. Okay, so you remember that a damping factor less than 1 is an underdamped system. Any questions about that?
Less than 1.
Just about putting the numbers in, really. Of course, you can get MATLAB to do that. The only slight thing with MATLAB, it doesn't use natural logs, it uses log as the natural log. I'm not really sure why. Okay, so I haven't done this in the MATLAB file. You can add that if you want. Does everybody wait a few minutes to finish copying that?
Where did you see that equation was lost? Is that in the book?
Yeah, it's on page 180. If you've got the same version of the book as me.
180.
180, yeah. Again, you wouldn't need to remember this, by the way. Don't worry about remembering equations like that for the exam. You wouldn't be expected to remember that. It's too long. There's one little green button.
Oh, she's right.
Yeah, you found it. Okay, can I carry on?
Mm-hmm. Aye, aye.
Okay, let's go back to the file. Okay, so that I've done that separately on a calculator, obviously. So this is the zeta value for an overshoot of 20%. So if any of you are lucky to have 20% in your column, you know what your answer is meant to be. Okay, and this is the way we write the transfer function. I don't know if I've shown you this before, but that's the open loop transfer function. TF just stands for transfer function. It's quite similar to simulate. Top line is your numerator in terms of the biggest values of s, powers of s first. So for this one, we've got s plus 8. So you can see 1/8 is the s plus 8. And then on the bottom, if you multiply those out, you've got 1, 19, 108, and then 180. That's straightforward. You can see that okay? Yeah, that's straightforward. Okay, and then the next thing is to get MATLAB to plot the root locus for us. So this command here does that. And as I said, make sure you change your comments to suit what you're doing. But, and then this next line here, s grid zeta comma 0, that adds your lines of equal damping. In this case, damping of 0.456, constant damping. You don't need to do this, adjust axis limits. You can ignore that. You can do it if you want it. You can zoom in on the plot after you've plotted it. So all that does is just brings the point of interest straight onto the screen. But you can obviously move your plot once you've got your plot. So, in fact, I might just comment that out and see what it looks like without running that. Okay, what I'll do now, I think, is run this. I had actually sectioned it for the other group, but I'll run this. And you'll end up with 6 plots coming up. But the way it works is you only work on the first plot. You get your value, you rerun it. And then you work on the third plot. You get your value, you rerun it, and so on. Okay, so to run this, you just need to press the run button, hopefully. You need to have the folder pointing to the right thing, so I'm just going to say change folder there. But it's not as critical as with your Excel stuff, where everything had to be in the same folder. This runs by itself anyway. Is that actually working or not? That's actually doing anything. No, it says it's busy. Okay, it is working. Okay, so we can ignore most of the figures for the moment. The only one we're interested in is this first one. So what this is your root locus of plot of the poles. In fact, this root locus also shows the zeros, but we're not really interested in the zeros. We're only interested in the poles, which are coming in like this, and then going down, and coming in like this, and then going up, as k changes, as k gets bigger. So, for instance, that might be at k equals 0, and this will be at k equals 500 or something, I don't know, whatever value. So this here, this diagonal line, is your point of constant overshoot, or zeta. So what you want to do is you want to put a point on there, and you want to preferably get it a bit more accurate. I won't do that just now, but you could zoom in, put your point on the point where they intersect, and you can read off here the gain. I'm wondering how we're doing for time. No, we're okay. So this would be essentially a proportional gain that you're going to add to your system to get that particular overshoot. The other thing to take note of is just this value here, because that's actually the coordinates of this point. So it's minus 5.42 on the x-axis and plus 10.6 on the y-axis. Does that make sense?
Mm-hmm.
Yeah, still following that? Okay, so we just read this gain, 1, 2, 2. I might have a slightly different value because I might have done it more accurately, but we'll never mind about that. Yeah, so when I read it last time, I had a slightly different value because I maybe zoomed in a bit more. So these were the coordinates of that point, and that was the gain at that point. So obviously you've got to tell MATLAB what value of proportional gain you want to use. So that's what this line here is doing. Just saying I want to use this value of gain because this gives me the intersection with the overshoot of my spec. And then, of course, that's just an open loop system. That's just, if we flip back to here, that wasn't the right thing. That's the thing I drew. I drew this. Did I rub it out? Okay, yeah. So that's just an open. That's just this, with this gain. So we need to add the closed loop feedback here, and it's just a single command to do that. It's quite easy. It's just this feedback command. Okay, so what that's doing, it's multiplying K1, which is our P gain, times our transfer function, and then it's putting in a feedback of unity, making it into a closed loop system. And then we want to, meanwhile, if you look at the command window, I've set the program so you can see what's going on in the command window. Command window being here. So you can see all your different transfer functions being calculated in this command window here. They're just for interest. You might want to put them into your report. Anyway, and then the next bit is to plot the response. So you can define a figure number, or you can just write figure for a new figure. So otherwise it will rewrite over figure 1, which you don't want it to do. And then you can do a step response just with this command here, step M1. That applies a unit step to your new system, M1. And you end up with a response that maybe looks a bit like that. Okay, so you can add some points to that. The easiest way to add the points to get more accurate measurements is to right-click and then to select characteristics and look up for the things you're interested in. So we're interested in the peak response. So I'll put a dot there. We're also interested in the steady state value. And then if we click on that peak response, we can measure some various things. So things we're interested in, overshoot should have been 20. It's a wee bit above that. Maybe I misestimated the point slightly. But it's quite close to the spec. You can see that actually worked quite well. And the other thing was the peak time, which is out of spec. In our case, we're looking for 0.2 for the example. So that's over the value, so we need a derivative controller to improve that. And the other point here, the steady state value, 0.84. We've been putting in an amplitude of 1, so we have an error. So we're going to need an integral controller to get rid of that error. Okay, is that making sense? I might go over this again, because I know we've had quite a long morning. Well, I suppose you can play the video. Quite a lot to take in one day. So anyway, I've put in some comments just saying what we got, whether it met the spec or not. You can change those to suit yourself. The derivative controller design is more complicated, but you don't really need to understand it. You just need to be able to put the numbers in and follow the steps. So the first thing we want to do here is to measure the angle of zeta. Now in this case, our damping factor is 0.456. So that is shown on our graph here. Yeah, this sort of very light dotted line is our angle. So what we're trying to find out is this angle here. So you can do that by trigonometry. Yeah, if you know the coordinates of this point, I don't know if it will let me write on this one. It'd be good if it does. Yeah, so you can make a triangle with that point, yeah? Where we know that that's 5.42, the length of that line, and the length of this line is 10.6. Must be a different scale. It doesn't look like 10.6, but anyway. So we can work out this angle with our SOHCAHTOA formula, yeah? So tan to the minus 1 of that angle is opposite over adjacent. Yeah, agree with that?
Agree.
Yeah, quite easy. And then we can work out the value of this angle. How would I do that? Yeah. So that's easy, isn't it? So what we're looking for is this angle here. That's the angle that the MATLAB file is talking about. You can either do that or you can measure it, but I guess if you do it by maths, I'll give you more points than if you take a protractor. So what the derivative controller is trying to do is trying to add a zero that compensates for the effects of all the other poles and zeros in the system to try and improve that rise time or peak time. It's a little bit complicated, but MATLAB does it all for you, so it's not really too big a deal. And you can follow it through in the book as well. Okay, so for this system, we ended up with that angle being 117 degrees, that phi angle I showed you. So there's some straightforward equations. This one is working out the imaginary point of all the poles and zeros together, what they call a compensated pole. That's not actually the equation. The equation is actually pi divided by peak time. Okay, I don't know if I can write that on there just now. I might be able to type it in. Pi divided by peak time. Okay? So that's what you'll be using. You won't be using this pi over 0.198. You'll be using pi over peak time. So that gives us a value. That's the imaginary axis value coordinate of that compensated pole. And then you can work out the imaginary part, again, using the same sort of idea. This equation actually is P imaginary divided by tan of the angle, yeah, that you just calculated. That wrong, I did two D's. Okay, so this is the tangent of that angle. The D part just tells MATLAB you're working in degrees rather than radians. MATLAB always assumes radians if you don't tell it. So the D is just for degrees, and the top bit's obviously the bit you worked out up here. I'm not very sure why I wrote it like that. It must be the way the book did it as well. Okay, so now we've got some values. We've got 15.87 for this particular example, a minus 8.13. Actually, when I was in China, I went through this example with them, and I had to keep stressing, this is an example. Please don't hand me the same coursework, because their English was so poor. I thought, I'm going to get a whole 100 courseworks that are going to be identical to this example. Hopefully not, but I'm not sure if they understood or not. Anyway, you guys understand this is an example. Don't give me the same numbers. Okay, and then we're going to get MATLAB to work out the sum of all the poles and zeros angles to this compensated pole. So this line here is doing that, okay, or these two lines. You don't actually need to change that first line at all. And this second line is your transfer function. Okay, so this first part, which is positive, this is your s plus 8. In your case, it will be a different transfer function, yeah? So that was the s plus 8 from the transfer function, and then this is the denominator, s plus 3, s plus 6, and s plus 10, which we had up here. S plus 3, S plus 6, S plus 10. You follow that? I do need to show you something else. If you end up with a transfer function that's just like this, that's really hard to factorize to get it into this form. So you can actually use MATLAB to do that for you. I'll just show you that just now. If we copy this, I'll put that into the command window here. Scroll right down to the bottom. So just type that in. You need to take the brackets S part out. MATLAB doesn't like that. In fact, it's not going to like any of this. I'll have to do it as a transfer function. I've got this done already somewhere. I think I've already got this. Sorry, I'm going to copy something different. That wasn't a good one to copy. Here. Let's copy that. That's better. Okay, so that's our transfer function, and we can run that. And then you can find the factors by doing a poll command. Hopefully. Yeah. So that's a nice, easy way for you to do the factors, okay? These are the poles, so that's why they've got negative signs, but you know that that relates to s plus 10. Because remember, your poles are when the bottom line's 0. So to make s plus 10 0, you have to make s minus 10. That's the only reason there's minus signs there, but you can use them. Okay, so going back to the MATLAB equation, down here, like I say, you just use that as it stands, but change these values. That's your numerator, and that's your denominator, once they've been factorized, in terms of s plus something, yeah? Run that, and we get an angle here. We should have got that, I think, that should be P angle. So if I go back to the command window, somewhere in the screen, we've got something called P angle. Yeah, so it comes up on your screen for you to make it easier for you to find. As long as you don't comment out that line or anything. And then we subtract 180 from that. And that gives us a new angle called C angle. Just gave them arbitrary names, you can call them what you want. And then we can work out the value of the 0 that we're going to add, which is our derivative controller, essentially. Our derivative controller is adding a 0, which is going to be at this value ZC. Okay, and again, it's just straightforward. Just copy the formula. The only thing is you'll have a different number in here, and the other numbers you've already worked out. So that came from that angle there. Quite easy, really. Like I say, you don't have to understand it in huge detail, just have to be able to use it. Okay, so then this gave us a new, a value for a pole, a value for the 0, 55.91. Then of course we have to add that into our system, because we're wanting to add this part now. And unfortunately, when we add that part, we have to change the value of this P part as well, because the gain changes. The root locus changes because we've added a 0, so the system changes. So we need a different P value. So we're just going to use the same process again. First thing is to define that 0 as a transfer function. So that's essentially our derivative transfer function there. And then to add it into the system. Okay, now I've not done that in MATLAB, which is a bit confusing. But basically, the equation is that. And you should be able to do that with MATLAB. I've done it manually for some reason. Maybe it didn't work. So all I've done is actually multiplied that s plus 55.91 by times s plus 8, which was my numerator. Okay, but you should be able to get MATLAB to do it automatically for you with this sort of command here. And this is the new transfer function. You'll see the denominator hasn't changed because we multiplied a numerator, a 0, not a pole. Then we're just going to do the same thing again. New diagram, plot the root locus, put on our zeta diagonal line and find the point. So that's already been done because I ran it. So this is figure 3. Okay, so this is now a system with a derivative controller and our transfer function cascaded together. So again, we just find the point where they cross, and we can get a new value for the new system gain, which in this case is only going to be 5. It's quite a lot smaller than last time, yeah? Then the next step, step 16, is to add that gain in. So now we have a PD and our G function. Going back to here. So that's P will be 5.32, D was this S plus ZC, and our system's originally this system. I don't know if you're going to make any sense of this when you read the video back, but never mind. And then add the feedback, which is the same command as we used before. Yeah? I'm pretty sure you're probably not following this by now, but I'll keep going through it because you can always play it back, if nothing else, yeah? Anyway, so there's our feedback added, unity feedback, and then of course we want to check whether it meets the spec or not. Do you think it's going to meet the spec? No, because we have... We need the integrator, yeah. So some people are still following. John's still following anyway, so that's good. Okay, so we do our quick check of our system, which I think is figure 4. Again, we can quickly put the peak response on. We're not interested in steady state because we can see it's not reached that anyway. But so it's quite close to the overshoot. It might not be exactly, but it's pretty close. But you can see here the peak time's gone down quite a lot. So we're actually meeting the peak time response now, which is the main reason for adding the derivative controller. The peak time spec for this one was 0.2. So that's actually been met. But of course here, we still have an error. So we need to add the integral controller. You'll be glad to hear the integral controller is really easy. The integral controller can always just be this transfer function. The reason for that is what we ideally want is to put a pole at the 0 point of our graph. So going back to our graph here. I'm sorry, that's the wrong thing. Here. Let's go back to that one. Doesn't really matter which one. So ideally, an ideal integrator would be a pole at that point. Now, the problem with adding a pole at that point at this stage in our design is that it's going to affect all these angles we calculated here because it's a new pole. So, you know, I was saying that this compensated pole is the sum of all the poles and zeros in the system. If we add another pole, we'd have to go back and recalculate all this. So that's not very easy to do, and it's not ideal. So we can get around that by adding a 0 very close to that new pole. We can't add them right on top of each other because they would cancel each other out, and then we'd have no integrator again. But if we add it quite close, it doesn't totally cancel out the integrator, it just cancels out the angles, so that all the angles add up again. So we don't really need to redo this part. So the book suggests just put a 0 quite close. In this case, we've got S plus 0.5, which is quite close to 0. So that transfer function there is actually S plus 0.5 over X. So the denominators are in your pole, and the 0.5 shows 0. And that's only to cancel out the angles so that you don't need to redo it. Right, then we combine them all together. So now we've got 3 things in cascade. Well, actually, we need to recalculate P, but we've got D, I, and G in cascade, which is what this gives us this transfer function here for this example. And then we've got another root locus, because the last thing we need to do is get a new p-value for the new system, the system with the di and the transfer function. So new root locus, at that point we should get a plot that looks a bit like that. So we can work out another p-value. So I just put another dot on there. Again, where they intersect, the 2 lines intersect. So we end up with a gain of 4.7 for this system. So that'll be our p-value for this system. And then the last bit is just to add those all together. I got 5.05 last time. I probably zoomed in a bit better. So new gain value. This is our complete system with the I and D parts. That's the new P part. That's putting it into a feedback loop. And the last bit is to get the step response of that new system, which gives us that. Okay, and then we can do a bit of analysis on that. and hopefully our system should have met our specs. So we've got 15.4 overshoot. Our spec was 20, so that's fine. You always want the overshoot to be less, of course. I'm sure you understand that. You don't want like 20, it's a maximum of 20. So 15.4 meets the spec, 0.18 meets the peak time spec, and you'll see here it hasn't quite settled, but actually it's going to have, when it does settle, it's going to have no steady state error. So this is a fully designed controller that would meet our requirement. Right. Okay, when you do this, you might find that your controller doesn't quite meet the spec. You can play with this final K value. The easiest way to tune it is to just change that K value until you get something that's close to the spec. Okay?
I thought there was meant to be no steady state error.
There isn't. It just hadn't run it long enough.
All right, okay.
Yeah, if I ran that for longer, you can see it's still changing very slightly. You go back to, but well spotted, yeah. You can see it's still rising. I guess if you ran it for another.
So we'd actually have to run the program, keep it going for a while in order to get. Is that what you mean?
You could just change this time base. Actually, I'll show you how to do that. Properties. Probably easier just to stick with the program as it is and then zoom in or out on the graph as you need to. So the easiest way here would be to probably change your x-axis. I don't know, what do we put in? 50 maybe. Well, okay, this one still has a tiny steady state error, but it's very small. I guess you could just.
It's not good enough.
No, it's not good enough, is it? So you can say that. If your system doesn't meet the spec, you can analyse that and evaluate that in your report. Yeah? You might also find that it's very hard to get this to the right peak time and overshoot. Because obviously, as you decrease the peak time, the overshoot gets more, and vice versa.
What does the arm to the end?
The last little bit, hold up for a minute.
994
The last little bit of this coursework, which is where I'm expecting. So you're all going to have kind of similar results up until this stage. Yeah, obviously you've got different transfer functions, but you're going to have quite similar MATLAB file comments and all the rest. But the last bit is I want you to do some critical comparison. You listening, guys?
Yeah.
I want you to do some critical comparison of the controller you designed last time in coursework A with this controller. So you can think of anything that you think might be relevant. Could you do this process with a real system? What would happen if it wasn't totally accurate? How easy is it to understand? How difficult is it to do? What would you do if you didn't have a MATLAB program? Could you still do it? Is quarter amplitude response good or bad? You know, just come up with as many different things you can think of and argue your point, either based on something you've seen at work or on what we've done in theory, or just your general opinion. You won't lose any marks for something that doesn't really make sense, as long as it's not completely stupid. But you will lose marks if you just write me 1 or 2 lines and just say, I think this root locus is better because you can tune to a spec. That's not a good critical argument. That's not going to give you any marks, really. So I'm just looking for you to think of all the different things that might actually affect a real controller. Environment, accuracy, ease of tuning, difficulty of tuning, understanding of the process, teaching someone else to tune it, anything like that, yeah? Get the idea. I'm guessing it'll be a few weeks before we get to that stage anyway. Right, that was quite a lot.
Were you killing us?
Yeah. So, as always, there'll be weekly self-assessment questions you should go through because it's building up your knowledge for the exam. And you can start this coursework anytime you like. If you can try and do the coursework in class some of the time, that would be quite good because I've no doubt you're probably going to have problems in MATLAB. There's going to be little bits that won't work because you've not typed something in quite right or you've edited something wrongly. So, yeah, I'm here to help you if you're doing MATLAB here. It's quite hard to explain what's wrong with a MATLAB program if you're not here. Sometimes. Sometimes it's really easy. Just use capital letters and small letters instead. But not always. Right, is everybody reasonably happy? I know this is a tough subject, but this is the hardest bit done now. the rest of it's pretty easy. Okay, you can have a break and then you can come and start. Take it, no one's got any questions. Understand it. It doesn't exist super often.
This call has been disconnected. Thank you for joining.